Good evening all. In this particular lecture, see, in the previous video, we have done till the mapping. If single point we have to map from S plane to W plane, then what are the properties and what is the meaning of mapping that we had seen. Actually, when we are going to talk about the Nyquist plot, or Nyquist, what we can say. Drawing the plot and then talking about the stability. So to reach that, this principle which we are going to discuss now is very important. So we know the mapping. Actually, we are doing plotting the Nyquist plot means we are trying to do the mapping only from S plane. So whatever is the contour in the S plane that we are going to have, that is this one, right? This thing starting at this point, going over here, coming back, and again over here. This is a Nyquist contour, and this will be in the S plane, and mapping of that will be in the W plane. So what will be the mapping? That will be the this will be in the W plane, and this is called as Nyquist contour, and this one is the Nyquist plot. Correct. So from S plane, with some set of points we want to go for Nyquist plot. So after drawing that, what we are going to achieve, and if we are doing this contour means a closed path, or we can say a locus of points, right? So when we are going like this, so in general in S plane, what are those conditions, or what is that principle by which if we are trying to draw Nyquist plot, whether we can claim anything, we are trying to see that thing over here. So let me start with, and then we'll come to know what is the need to talk about this. So the principle is called as Cauchy's principle of argument, or it is also called as Cauchy's argument principle. Both the things, or it is also just it is called as principle of argument also. So we are talking about some six normally used conditions to explain this principle. Okay, so first I would like to write all those conditions, and then one by one we'll discuss those. So number one, when you are drawing, when you are considering a contour in S plane, and let us say 1 0 is coming inside it. So I'll write 1 0 inside the contour. Then the next possible condition is one pole inside the contour. Then the third thing is no zero, no pole inside the contour. Then the fourth thing will say 1 0 and one pole inside the contour. Yeah. Then the next condition is fifth one, I'll say, when we are going to have two poles inside the contour. And last one, two poles 1 0 inside the contour. So when we'll discuss all these six conditions, the idea of this what we can say mapping will be very much clear to you, and I will try to show you one video also based on that. So definitely that will clear you how we are getting this and actually what is happening on the plot because of this. So every left hand side plane is S plane, keep this thing in your mind, and right hand side plane is the W plane. uh, every time now I'll not write it, I mean it should be understood, right? So first time I'll write over here and it is applicable for every plane now. So this is S plane and this is W plane. W plane, or you can say GH plane also. Both the things are same. We had seen this thing in mapping, right? What is GH plane? Whatever is your transfer function, in that you are going to put that value of S and you are trying to see how the point is getting mapped from S plane to GH plane. Okay, so we are talking about first condition where you are having a you are having 1 0 inside the contour. So let me draw any contour we are considering over here, any close path over here we are considering, and what we are trying to do, we are trying to move, let us say this point, and in the uh, clockwise direction. Now you may say why clockwise, why not anti-clockwise? Correct. But normally when we are going for the Nyquist contour, we are starting at this point omega equal to 0. We are going till omega equal to infinity, then moving towards this circular path considering the whole our what I can say right-handed plane, then going to omega equal to minus 90. So actually we are moving in the clockwise direction, and that's why while taking the example also, all examples I will try to discuss in the clockwise direction, so will be easy for us to understand. So this point we are moving in the clockwise direction, and we'll try to see what will be the mapping of this over here, right? So this is, and what one condition we are considering, yes, we are having 1 0 inside it. Okay, so let me draw that 0. Let us say this is the 0. Okay, now the second thing is, again I will draw the contour. It can lie anywhere in the S plane. Okay, I'm just drawing it over here. That means it will be in the first quadrant or second quadrant or third quadrant. It's not fixed. It can be drawn anywhere. Okay, so I'm just drawing it. Right. So the what the condition is saying? First one, 1 0 inside the thing, inside the contour. Second thing is one pole inside the contour. Third thing is saying no zero, no pole. Fourth is saying that 1 0 and 1 pole inside the contour. Second one, 2 poles inside. And third one is saying 2 pole and 1 0 inside the contour. Okay. Um, yeah, I should draw everywhere the direction that to be clockwise. So we are trying to move the point on the contour in the clockwise direction. So the direction of the contour is actually clockwise, that we are saying. Yes. Okay. Then the point that is there. So let us say this is the point which you are moving, and how this point is going to move in the W plane. That is the thing that we want to see. So see now, what we are we know that let us say we are having uh, poles, three poles, let us say, and one zero over here, right, in the transfer function. Now, when you are doing mapping of this point over here in the W plane, we had seen that we are supposed to draw the phasors, right, or phasor lengths from this point till this point, from this point till this point, from this point till this point, and from this point till this point. I'll dark that point again because it vanished because of the other vectors. Correct. Now, just see what is going to happen. The points which are outside the contour. Very well, you can see. I will try to draw that thing over here. If this is the uh, pole and this is the zero, right? Actually, what we are supposed to do, we are supposed to add all these angles, right? So zero ka angle minus pole ka angle will give you the actual angle of this in the W plane. And we had seen that whatever will be the angle, corresponding angle to overall phasor angle of this point with respect to all these zeros and poles in the system, the same mapping angle, the same angle will be there in the W plane, but it will be with respect to zero. So this point we are going to get with respect to zero, right? So first we would like to see if the point is outside the contour. Now how it is moving? See, if I am drawing the contour, this is the contour. Now what is happening? This point is over here. Then it is going up, right? Again going up, again going up till the top, right? So how the angle was in the angle was increasing in the clockwise, sorry, anti-clockwise direction. As soon as the points are downward, you will find now we are going clockwise, correct, till this point, lowest point. So how we are moving downward direction. Again, when this was the lowest point, for all these points after that, that means if I draw over here, again we are moving in the, we are going up, so again in the anti-clockwise direction. So half of the part we are moving in the downward direction, half of the part we are going in the upward direction. As we are moving from this point over the contour and again reaching to that, you'll find half of the points will be I mean whatever angles will be positive, those many angles we are going to have negative. So overall angle effect of this pole on the angle, right, while doing the mapping or finding out the phasor angle, you'll find it is becoming zero, because for half part it is zero, for half part it is sorry, for half part it is positive, for half part it is negative. But you just see the zero which is inside it. Now what is happening for this zero? It is moving only in one direction, and that is only clockwise, only in one direction and in the clockwise direction, right? And that's why you'll find this effect of all these things is getting nullified, and ultimately only angle because of this is remaining, and because it's a zero, it is going to come in the numerator. So whatever is the angle of angle in which, I mean the direction in which we are moving this point, so if it is going to be the clockwise, then the contour that we are going to get will be also clockwise. So I'll draw that contour over here. So the corresponding contour somewhere over here will get like this, and it is going to be in the clockwise direction only. Now see, if we are having one pole inside the contour, whatever rest of the things in the same condition what we had over here, whatever n number of things, n number of poles and zeros we are having outside the contour, everyone's effect will get cancelled out. Only effect of this will be considered, because again it will be only in the clockwise direction. As your contour is moving in this direction, the angle will also move in the clockwise direction. So it is going to be from 0 to 360, the overall angle, right? But because it is a pole, the pole is in the denominator, right? So it is having the negative sign when it will come in the numerator. It is the angle of the zeros minus angle of the poles. Pole is in the denominator and pole is from zero. Whatever is the angle of the pole, it is going to be when it will be in the numerator. Now 0 is not there, right? Everything is getting cancelled out. So actually it is minus p. So whatever will be the angle, if it is 30, in this case, then it on this side it will be minus 30. Correct? If it will be 60, it will be minus 60. And because of that, you will find that yes, again 0 to 360 rotation is there, but it will be in the anti-clockwise direction. So I would like to highlight those words. Okay. So here clockwise. Here it is anti-clockwise. Right? And the same line, when you are having not a zero, not a pole, inside the contour, so no 0 to 360 angle is going to come. Everything is outside, so everything will get cancelled out, and because of that you will find no rotation along the, I mean around the origin you are going to have. So you are going to get a contour, but definitely it will not be it will not be encircling the origin. Now, when there is one zero and one pole, effect of zero, and because zero is in the numerator, pole is in the denominator while considering the phase angle, or the yeah, phase angle when we are calculating, right? Uh, for 0 it is 0 to 360. For phase also it is 0 to 360 around the origin, but both are, one is positive, another one is negative. Everything will get cancelled out, and ultimately you are not going to have any rotation around the origin because of that. So whenever it is 0 or pole inside the origin, you will find yes, a rotation will be around the origin, otherwise not. Correct? Here it is there, but they are cancelling each other. Now we are having two poles. So one is adding to the effect minus p, one more minus p. So minus 2p. And because of that, you will find that we are going to have rotations along the origin, and it will be twice. So once in the anti-clockwise direction, once more in the anti-clockwise direction. Right? So twice you will find it is moving around the origin. Two rotations will be there around the origin. Okay? Because two poles and one zero, one pole and one zero will cancel their effect. Only one pole ka effect will be there, and that's why you will find one rotation around the origin we are going to have. And definitely because it's a pole, that's why it will be in the anti-clockwise direction. Pole will come in the denominator. Okay, so ultimately we reach to one conclusion or one principle, and that principle is, see, if I say number of zeros minus number of poles, right, that is giving me total number of rotations. Wait, I'll write it properly. Yeah, so n is equal to zeros minus poles. What is this p? This p is, otherwise equal. Mm, see. This p is OLTF poles. Z are OLTF zeros. And n is clockwise rotations around origin. See now, we'll try to see whether it is matching with the uh, whatever we said, right? See, Z in this case, Z1, right? And P0. So I'll write instead of that, we'll go by 111 condition and we'll try to write. So I'm talking about first condition, right? In first condition, you had Z1 and you had P0, and because of that, n ka value was 1 in the clockwise direction. In what we are saying, clockwise direction. So n was 1. Satisfied? Correct. Second one, zeros, no zero, pole, one pole, and that's why you got rotation but in the anti-clockwise direction around the origin. When it will be no zero, no pole, no rotation. Third condition. Right? Fourth condition, 1 0, 1 pole, 0 rotations. Then 0 zeros, 2 poles. So minus 2. So in anti-clockwise direction, 2 rotations. Correct? And the sixth one is 2 pole, 1 0, sorry, 1 0. So it will be 1 minus 2. So it is going to be minus 1. 1 in the anti-clockwise direction. Okay, so all these conditions are getting satisfied. So this thing, whatever I have written, uh, n is equal to z minus p, this is called as Cauchy's argument principle, or it is also called as uh, this principle of argument. Okay, so to uh, just to support this whatever I have told you, right, I'll try to show you one video, and definitely that will clear the if the doubts are there, the doubts will get cleared. Just a minute. See, this is by Brian Douglas, and he's trying to draw something for us in the MATLAB. Okay, just I'll switch on, and whenever I'll require, I'll stop and
What I mean using MATLAB again. I wrote a small program in MATLAB to give you a visualization of what I just drew for you. Here we have a transfer.
see. Now this is the transfer function which is telling us that s is equal to 0 is the 0, and in the denominator s square, that means two poles are there. So two poles are drawn over here. Just solve this thing, we'll be able to get those two poles. Right? So this is the s plane, this is the w plane or gh plane, and this is the origin of w plane, and this one is the origin of the s plane because s is equal to 0. Correct? And now this is the point which the brown point which I had shown. He will try to move this point, right, to complete the to show you the contour, and he will try to see what is the effect of that over here. So this point where these three arrows are meeting, that is corresponding in the w plane, that is this point. I'll switch on the spotlight. Yeah, right. So this point in S plane corresponding to that, the point is over here, right? So this thing, the distance from the origin is showing you the length, right? And this circle thing, that is showing you the angle. So when this point is at this point, at this particular position, the angle is actually minus 90. Now see, this angle and this angle, they are same and with minus sign, right? So if it is 30 or 60, whatever, so this will be minus 60. So they will cancel out each other. So what remains? Only 0. And 0 ka angle is uh, here angle is 0. Correct? So that's why with respect to this, if you'll consider from this 0 till this point, the angle that is drawn, correct, it is 180, not 0. Sorry, I made a mistake. So you can see from 0 to this point, if I'll draw phasor, it is this phasor, and then see the angle, it is total this angle, that is 180, and that's why from this point, the point is drawn at minus 180.
Transfer function with two poles and one zero. you see the exact function in the title. I've chosen a value of s right in the middle at s equals minus 2, and on the right is the mapping of that point into the w-plane. You can see very quickly that if we add the phase of the 0, which is 180 degrees, and subtract the phases from the poles, which is positive and negative of the same angle, so they cancel each other out, that the phase should be 180 degrees on the point on the right. And it is. Now let me move this point to a new spot in the s-plane. Now the phase from the 0 is plus 90 degrees, and the phase from the pole is maybe around 60 degrees or so. And therefore, 90 minus 60 is about 30 degrees, and that's again what we see of the point in the w-plane. Now if I sort of trace out a contour with this point, but make sure not to include any pole or 0, then the addition and subtraction of the phases will never go around 360 degrees. And you can see this very clearly on the W plot, that the phase just sort of hovers between 150 degrees and 210 degrees. However, if I do encircle a 0, then as we go along the contour in a clockwise direction, we'll be adding 3.
So see, it is around the zero, and the movement is clockwise, and that's why the point in the W plane is also moving in the clockwise direction.
360 degrees of phase as we move around the 0. This causes the point in the W plane to rotate 360 degrees in a clockwise direction, like our contour. And if I circle a pole, then we're subtracting 360 degrees of phase as we move around the pole, causing a counterclockwise rotation in the W plane. Now, I've written a second demo that might make this a little bit easier to see. Here I have a single pole that I encircle, and the resulting plot circles the origin one time in the counterclockwise direction since we're subtracting 360 degrees of phase. Now I'll add a second pole and rerun it. And as you can see, there's going to be 2 rotations around the origin, one for each pole. Finally, I'm going to add 2 zeros as well. And now the resulting plot doesn't circle the origin at all. And that's because we're adding 2 times 360 degrees of phase from the 2 zeros, but at the same time subtracting 2 times 360 degrees of phase from the 2 poles. Sure, the plot on the right, which is the green line, is still going to have a bunch of circles and squiggles in it, but it never encircles the origin, which is really important to note. And that is really
Right. So that's all for the mapping and the Cauchy's principle. The remaining part, that is the numerical and the use of this contour and all, right? We'll see in the next video.